So let's spend some time talking about the mole, defining what the mole is, understanding the mole, and then start using the mole for conversions and talk about some molar mass. First, what is a mole? The definition of a mole states that a mole is the SI unit for substance, the quantity of a substance that contains the same number of entities as the number of atoms in exactly 12 grams of carbon-12. The definition itself can be difficult for students to understand, so let's back up a little bit. A mole is a number word. What do I mean by a number word? I mean it represents a specific number of things, such as if I said 1 dozen eggs, I know that that means 12 eggs. If I said baker's dozen, I know that represents 13 of whatever I'm talking about. If I say a couple of tacos, the word couple means 2. So this would be 2 tacos. A gross of pencils. Now, less people tend to know what a gross means, but gross itself means 144. So this would be 144 pencils. So if I'm saying a mole of something, I'm saying a specific number of that item. It tells me it's the SI unit for substance. Remember, SI, that's our standard units. And so of a substance, the quantity of substance that contains the same number of entities as the number of atoms in exactly 12 grams of carbon-12. So if I have exactly 12 grams of carbon-12, I have 1 mole of carbon-12. But what is that number? That is what we call Avogadro's number. .022 times 10 to the 23rd. Now, you may see that written somewhere at 6.02. In my class, you need to use 6.022. It gives me 4 sig figs this way. And that's a really big number. If I took that out of scientific notation, it would be, and I have to do this by counting, 6022. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. I then go ahead and put all my commas in to separate out all my zeros, which are hard to see. 1, 2, 3. I don't think I put those in the right spot. 2, 3, 1, 2, 3, 1, 2. Oops. 3, 3, 3. There you go. Sorry about that. Just trying to show you like just how big this number really is. It's a really big number. That number is bigger and harder for most people to understand. That number is bigger than if I took the entire population of the world right now, we would have less than 1 mole of people. It's a very large number. But what does that number really mean? It means if I have exactly 12 grams of carbon-12 atoms, I have that many carbon-12 atoms. That's insane, right? That's a huge, massive number. But what I want you to think about is just how small a carbon or any atom is. Atoms are very, very, very small, smaller than we can see with our human eye without some kind of instrument to help. And honestly, they're smaller than most of us can really comprehend. It's just tiny. So it takes a lot of them to equal up to 1 mole of material. And so if I wanted 1 mole of particles, I would have 6.022 times 10 to the 23rd particles. If I want 1 mole of atoms, I have 6.022 times 10 to the 23rd atoms. If I have 1 mole of electrons, I have 6.022 times 10 to the 23rd electrons. And if I have 1 mole of molecules, I have 6.022 times 10 to the 23rd molecules. Again, 1 mole is representing a very large number for us, but it's specifically based on carbon-12. Why carbon-12? Because as we talked about previously, the entire periodic table is correlated or based on carbon-12. 1 AMU is equal to 1/12 of a carbon-12 atom. So the table has been normalized so that 1 mole is 12 grams of carbon. We figure out exactly how many particles are in exactly 12 grams of carbon. we find it to be 6.022 times 10 to the 23rd. We know how much 1 mole is. Also, this little guy here, this is our mascot from the American Chemical Society. It represents our mole. So how does this help us? Well, we can count atoms by using moles. If we can find the mass of a particular number of atoms, we can use this information to convert the mass of an element sample into the number of atoms of that sample. So let's go ahead and look at copper. I know that if I have 1 mole of anything, I have 6.022 times 10 to the 23rd of that thing. So therefore, if I have 1 mole of copper atoms, I have 6.022 times 10 to the 23rd copper atoms. But remember, when we have an equality like this, that is giving me a conversion factor. But I also know by looking at the periodic table. I can look at the table. We're going to talk about this as well. So we get atomic mass or molar mass. Atomic meaning for one atom, one type of atom. Molar or molecular mass. Molar mass, molecular weight, meaning for an entire molecule or compound. I know that 1 mole of carbon atoms will equal 63.55 grams of carbon atoms. Where do I get this number? Periodic table. We've already talked about how to correlate that number, how to develop that number with the isotopes of copper and the ratios of copper. So I know that that number is 63.55 is on my periodic table. I know I get that by looking at the isotopes of copper and how abundant they are. And I use their fractional abundance to figure out the overall number there. But that means that 1 mole of copper atoms weighs 63.55 grams of copper. So if I have 1 mole of copper atoms that contains 6.022 times 10 to the 23rd copper atoms, and it weighs 63.55 grams of copper. Just for visual on your side, 22 copper pennies contains approximately 1 mole of copper atoms. So if you have 22 copper pennies, you've got approximately 6.022 times 10 to the 23rd copper atoms. And this brings us to what we call molar mass. Molar means per mole. So the mass per mole. The mass in grams of 1 mole of a substance, and it's the average mass, because again, it comes from the relative abundances of the isotopes of that element. So the molar mass of copper is 63.55 grams per mole, meaning it takes 63.55 grams to make 1 mole of that material. So this is just kind of conversions that we can do. Now, I much prefer you do these as actual conversion factors, but students sometimes just getting practice and getting started need to see it a little bit differently. If you are going to try to convert between grams, molecules, atoms, particles, things, generally speaking, any of it, we have to go through moles. So every time you have to go through moles first. Moles is your middle ground. You cannot convert from grams straight to molecules, atoms, particles, or things. You cannot convert from molecules, atoms, particles, or things straight to grams. You have to go through moles first. So use your moles first. If you are going between grams and moles, you use your atomic or molar mass. Again, atomic just means for one specific atom of something. So like copper, carbon, nitrogen's a diatomic. Copper, carbon, zinc, sodium, any of that, that's atomic. Molar mass is for anything that's not a single element. So we've got diatomics, we're going to talk about in chapter 3. Like oxygen is a diatomic. It doesn't actually exist as just oxygen. The oxygen we breathe, it's actually considered O2. Carbon dioxide, carbon monoxide, sodium chloride, all of those would be molar masses because it'd be for more than one particle together. If I'm trying to go between grams and moles, though, I'm using my atomic and molar masses. So that, again, is listed as grams per mole. If I am going from moles to grams, so we can see the arrow here, I'm multiplying. And if I'm going from grams to moles, I'm dividing. Again, if you just do this as a conversion factor, you won't have to remember this and it will be easier. But some students, again, have to get a background down before they can do the rest. If I'm going from moles to grams, I am multiplying because a mole represents a very, very large number. A gram is more realistic to what we're going to see in the real world. We're going to multiply to get there. If I'm going from grams to moles, I'm going to be dividing because I'm going to represent something that's a very, very big number. A mole is a very big number. If I'm going between molecules, atoms, particles, and things, I'm using Avogadro's number. That is that 6.022 times 10 to the 23rd things per 1 mole of things. Whatever that thing may be, molecule, atom, particle, ion, compound, doesn't matter. And same thing we see if we're going from moles to molecules, atoms, particles, or things, we're multiplying. If we're going from molecules, atoms, particles, or things back to moles, we are dividing. But again, I recommend just doing its conversion factor. It will make your life a lot easier, and you will get the question right more often than not, if you're doing the rest of your stuff correctly, that is. But again, this is grams per mole as a conversion factor, and this is Avogadro's number as your conversion factor. So let's go ahead and work an example. What do I mean by this? Well, how many molecules are present in 2.35 moles of molecules? We're going to do the same thing that we started in chapter 1 when we do dimensional analysis. First thing we're going to do is write down what we're trying to find. If we read the question, it's asking us for molecules, and it's telling us we're starting with 2.35 moles of molecules. So I want to know the number of molecules. Write down what you're trying to find. Next, write down what you are given. 2.35 moles of molecules. Now I'm going to think about my conversion factors. I am trying to get rid of moles of molecules. I'm trying to get to molecules. The one conversion I have that goes between number of things and moles is Avogadro's number. I know that 1 mole of anything is equal to 6.022 times 10 to the 23rd of that thing. So 6.022 times 10 to the 23rd molecules for every 1 mole of molecules. That cancels out my molecule. That cancels out. I apologize. That cancels out my moles of molecules and gives me my molecules. Calculate that out. And so in your calculator, be careful, depends on what calculator you have. You are typing 2.35 times 6.022, and you should have some kind of E button. Most of the time it's a double E. This E and these E's are not the same E's. This is a natural log thing. Most of the time you're going to see it with a button like that. Do not use that button, please. That is not correct. Like that, or it may say E to the X. That is not the correct button. But EE, 23. That's how I'm able to type it in my calculator. I actually have to hit the second button to get that E button to activate. So you're going to have to try to find your scientific notation in your calculator if you don't know where to find it. 1.42 times 10 to the 24th molecules. And so we have our final answer. Now what about this next question? Number of moles of atoms. How many moles of atoms are present in 9.5 times 10 to the 15th atoms? So we want to know number of moles of atoms. And we're told we have 9.5 times 10 to the 15th atoms. Using the same conversion here, I've got number of things, and I'm trying to get to moles of things. My numerator, I'm going to put what I'm trying to get to, number of moles of atoms. My denominator, I'm putting what I'm trying to get rid of, 6.022 times 10 to the 23rd atoms. How do I know it goes in the denominator? Because if something is in the numerator and in the denominator, it cancels itself out. I also know I'm trying to get to moles of atoms, and by putting it in my numerator, it now gives me my answer in moles of atoms. Calculate that through, and I get 1.6 times 10 to the negative 8 atoms. And I forgot to discuss sig figs here, but let's go ahead and do that really quickly. So in this question here, this had 3 sig figs. So my final answer had to have 3 sig figs. Remember the times 10 to the 24? That is just your scientific notation. That is not your sig figs. Second question, 9.5, 2 sig figs. Again, that 10 to the 15th is telling you how big the number is. It's not your sig figs. 9.5 is my sig figs. My final answer, 2 sig figs as well. So 2 sig figs in my measurement, 2 sig figs in my final answer. I'm using Avogadro's number to 4 sig figs, so that will not limit my calculations. So we've talked about converting between moles and atoms of things, but what if we want to start using it for actual elements? How do we do this? Well, the mole, this word mole, relates to mass. 1 mole of carbon, if I look at the periodic table and I look up carbon, I'm going to find a box that looks something like this. It's going to have a C in the middle, it's going to have a 12.01 in the bottom, and it's going to have a 6 in the top. And we talked about this. We said, you know, up here is your atomic number, which tells you your number of protons, tells you number of electrons in a neutral species. This is your elemental symbol. And this is your average mass. But this also tells you your moles. So you may see it say 12.01, it may say 12.011, depending on how accurate your table is. Some go up to 6 decimal places. But 1 mole of carbon is equal to 12.01 grams per mole. So this number down here is telling me how many grams do I have in 1 mole of that substance. If I wanted to add up the molar mass of water, I would look up on the table. I would find that hydrogen. I'm going to pretend that's a box. Has a 1 and a 1.008. And if I looked up oxygen, (15.999), or some will just say flat out 16. Remembering our formulas, I know that water, H2O, has 2 hydrogens, so this would be 2 times 1.008 grams per mole. 1 oxygen, 1 times 15.999 grams per mole. Add this all up, and most of the time, oops, too big. And so it matches my answer, so I don't want to recalculate this right now. I'm going to most often write 16 grams per mole, because most tables you're going to see, they'll either be 15.99 or they'll just be a flat 16, but a 16 is what I have memorized here. And then I don't have to calculate things quick. But this, adding up, would give me 18.02 grams per mole water. So, I apologize. That means that 1 mole of carbon is 12.01 grams. 1 mole of H2O is 18.02 grams. But that gives me my conversion factor. That means that 1 mole of carbon, 12.01 grams of carbon. 12.01 grams of carbon to 1 mole of carbon. Same with the water. 1 mole of water, 18.02 grams of water. 18.02 grams of water to 1 mole of water. What if I look up at the one down here? Aluminum sulfate. Let's go ahead and, I gotta move this screen up a little bit. Let's go ahead and add this up. If I look up aluminum, 2 aluminums would be 2 times 26.98 grams per mole. Again, I'm getting that 26.98 from the periodic table itself. When I look up aluminum, that's what I see. I've got, so the 2 goes to the aluminum here. The 3 goes to this entire polyatomic, meaning I have 3 sulfurs. 3 times 32.07 grams per mole. And 3 times 4 oxygens, 12 oxygens, 12 times 16.00 grams per mole. When I add all of this up together, I get 342.2 grams per mole. So 1 mole of aluminum sulfate is equal to 342.2 grams of aluminum sulfate. So if I had exactly 342.2 grams of aluminum sulfate, I would have 1 mole of that material. Molar masses are really useful because we can use these to convert from grams to moles and moles to grams. Again, this is called molar mass. You may also see it called molecular weight, molecular mass, formula weight, formula mass. It represents the mass of 1 mole of material. The difference between molecular and formula, we're going to talk about this a little bit in the next chapter. But when we have ionic compounds like, say, sodium chloride, NaCl, this is a formula unit versus water, which is H2O, is a molecule. And so what that means is sodium chloride, it's not just one sodium ion and one chloride ion that hang out together. That's the way we write it for simplification. But really, it's a huge array of compounds together. It's an alternating pattern of sodium chloride, sodium chloride, sodium chloride, sodium ion is what I mean by that, but sodium ion chloride and sodium ion chloride ion alternating in a huge 3D crystal structure. The simplest unit of that is one formula unit, whereas water is one individual molecule. There's water molecules that can hang out together, but it's one individual molecule. We'll talk about more of that in chapter 3, though. That's why you'll see things like molecular mass versus formula mass. And a very useful formula for molar mass is remembering its mass over number of moles. Now that may seem intuitive because you're like, well, you just told me that. Yes, but there will be example questions we do where the question says you analyze this mass sample, and through the math you can find the moles of that sample, and then with that information you can actually figure out the molecular weight of the compound itself and identify what your unknown would be. So let's work a few more examples. What is the molar mass of ammonium nitrate, NH4NO3? If I got ammonium nitrate and it gives me my formula, I see I have 2 nitrogens, 2 times 14.01 grams per mole. This gives me 28.02 grams per mole for the nitrogen. I've got 4 hydrogens, 4 times 1.008 grams per mole. Gives me 4.032 grams per mole, my sig figs, and 3 oxygen, 3 times 16 grams per mole is 48 grams per mole. Sum this up together. When I put this in the calculator, I get 80.052. That is grams per mole. But again, I need to look at my sig figs here. This is precise to the hundredths. This is precise to the thousandths. And I forgot to mark up this is precise to the hundredths, meaning my final answer is hundredths. So my final answer here is 80.05 grams per mole. And it's usually sufficient to leave your molar masses to 4 sig figs overall. No, if you ever have a measurement that's more than 4 sig figs, you should measure your molar mass out to more sig figs as well to not let your molar mass limit your sig figs in your calculation or limit your precision in your measurement. But most often 4 will be sufficient for what we do. Let's see, we've also got calcium permanganate, CaMnO42. We've got 1 calcium. Again, there's no subscript here, so that just means 1 calcium. I look up calcium on the table and I see its atomic weight is 40.08 grams per mole. Now this 2 here applies to the entire polyatomic. So I've got 2 manganese, 2 times 54.94 grams per mole, 109.88. I'm going to underline my sig figs there, grams per mole. Calcium, of course, being 40.08 grams per mole. And 2 times that entire polyatomic, but I've got a 4 here, meaning overall I have 8 oxygen, 8 times 16 grams per mole. Gives me 128. I got to put the 0.0 there to keep my sig figs. Grams per mole. That happened up here on oxygen as well. Make sure you're not letting your sig figs drop. Sum this together, and I get 277.96 grams per mole. But hundredths place, tens place, tens place, I have to limit this to the tens place, so I'm going to have to round. I'm going to have to cut my number right here. I'm dropping a 6, I need to round up. This is going to round up to 278.0. I need to include that 0.0 to keep my significant figures in place. Molar mass, 278.0 grams per mole. For a lot more practice, we're going to do a lot more practice in the next video, but this is just kind of give you guys a basis to start.